Alright, looks like we are live. Welcome everyone to the Math2501/2601 seminar part 1. Part 1 will be presented by me and Lachlan Tobin, so I'll be presenting like the first hour and Lachlan will be presenting like the second hour. Okay. First things first is the attendance form. So I'm not sure how many of you guys are live right now, but whether you're live or watching the recording later, could you guys quickly scan this QR code just to fill in your attendance? It'll take like about 20 seconds or so. I'll give you guys about 20 seconds to fill this one out. Alright, let's move on. So I'm going to be presenting the first two topics, group theory and vector spaces. Now, group theory is for Math2601 only, so if you're doing Math2501, you don't need to worry about this first topic. But obviously, if you're interested, you can just tune in and learn about some groups and fields. Alright, part 1, group theory. Now, the very first thing we learn is the definition of a group, and a group G is specifically a non-empty set with a binary operation, usually just star, defined onto it. And they have to satisfy 4 conditions. First one is closure. So if we take any two elements in our group G and we apply the star operation to it, so A star B, that final element has to also be an element of G. So that's going to be the closure. Associativity, well, if we take A star B and then star it with C, that should be the same as A star, and if we take B star C. Okay, so the order in which we do the multiplication wouldn't matter, and that's for any ABC in G. Okay. Existence of the identity. Now, every group, there must be some identity element in it, we call it E, such that if we take A star E, that's the same as if we take E star A, which is just A. Okay, that's for every element A in G. So if we consider our regular multiplication, our identity element in that case would be 1, because 1 times any number is the same as any number times that 1, which is that any number. Okay. And our last one is the existence of inverses. So for any element in G, there must exist some inverse, let's call it A to the power minus 1, in that G, such that if we multiply the two elements together in any order, that returns us the identity element E. Okay. So again, thinking about the real numbers, if we have like the number 2, the inverse of 2 would be a half, because if we multiply half by 2 in any order, that returns us 1. Okay. And if we have the following condition met, we call the group an abelian group, and that's if we have commutativity, and that for every element A and B. If we take A star B, that should be the same as B star A. Okay. And if that condition is met, we call it an abelian group. And the group is denoted as the set G with a binary operation star assigned to it. Okay. So quick example here. So suppose we have a set G denoting the elements of 2 by 2 matrices in this form here, where you have X in the top left, Y in the top right, minus 3y in bottom left, and X plus 2y in the bottom right. And we have to exclude the zero matrix. That would get obvious in a second. So G is a set of all non-zero matrices in this form here, and we want to prove that G is a group under matrix multiplication. In this case, we're saying the operation star just multiplies 2 matrices together inside that group. Okay. Now, first thing we're going to look at is the determinant of this of any element inside G. So if we take any element x, let's just take this example here. We have xy minus 3y and x plus 2y. We find the determinant of that. That gets us x times x plus y minus y times minus 3y, and that simplifies down to x plus y all squared plus 2y all squared. Okay. Now we know that x must be non-zero, which means that x and y must be non-zero. Okay, and if x and y are both non-zero, that means that the determinant here can never be zero, because we have a sum of squares, and the only time this determinant is equal to 0 is when y is equal to 0, and hence our x is also equal to 0. But that can't happen because we exclude the 0 matrix, right? So the determinant is never 0, and that tells us that G is the set of invertible matrices. Okay. And again, first thing we check is closure under our matrix multiplication. So for this first condition, we always take two arbitrary elements from our group, P and Q. So we just let P be this matrix here, replace like the x and y's with a and b's, and Q we replace the x and y's with c's and d's. Okay, and what we have to check is that if we multiply these two matrices together, it's also in the form of this expression here, excluding the 0 matrix. Okay, so multiply the two matrices together. I'm not going to go through like the nitty-gritty algebra, but this is what you should end up with. And again, we want to chuck this in the form of our definition over here. So we have xy minus 3y and x plus 2y. Okay. Now, we can do this by rewriting PQ in this form here, where we have this element here is x, this element here is y, this is minus 3y, and this is x plus 2y. Okay. And one thing that we have to check is that this here is non-zero, right? Because our G excluded the 0 matrix. But we can easily check this by just looking at the determinant of two matrices. So because we know that the determinant of any element inside G is non-zero, then the determinant of the product PQ, that's also going to be non-zero, right? Because if we want this determinant to be 0, then either one or both of the determinants of P or Q has to be 0, but that can't happen, right? So PQ can't be the 0 matrix, as the product of two invertible is also invertible. That's like, we can just look at the determinant in this case, and thus G is closed under matrix multiplication. Okay. That is the first condition. Now let's just look at the second condition. Well, we know matrix multiplication is associative, so we don't have to prove that. Usually, in the exam question, they'll tell you that you can just assume matrix multiplication is associative. Just skip like this nitty-gritty proof. Okay. Part 3 is the existence of identity. Well, we can just select the 2x2 identity matrix. We know that identity multiplied by any matrix is just that any matrix there. So if we choose, if we go back, if we select x to be 1 and select y to be 0, that would get us 1, 1 in the diagonals and 0, 0 in the other diagonal. Okay, that gets us the identity matrix. And we know that identity multiplied by any matrix is just that, any matrix. And furthermore, the existence of identity means that G is non-empty, because remember that the definition of a group requires a non-empty set. Okay. And again, last one is the existence of inverse. Well, 2x2 matrices are really easy to invert. We just divide it by the determinant, swap these two elements together, and chuck a minus sign in front of these two other elements. Okay. And we know that, again, the inverse must exist because the determinant is never going to be 0, right? And we get we get this expression here. Again, this is your x, this is your y, this is your minus 3y, and this is your x plus 2y. So we're chucking in a form of the definition in the group there. Yeah. Again, x inverse is never 0 because it has to have like an inverse. Okay, and we've proved that the 4 conditions are true. Therefore, G is a group under matrix multiplication. Okay. Now, some useful properties of groups that can be proved using from the definition of the groups. Well, suppose that we have any arbitrary elements A, B, and C in the group with binary operation star. Well, the first thing is that the identity and the inverses of each element, they are going to be unique. Right? So that means we can only ever have one identity element and one inverse for every element in the group. Okay. This one's pretty intuitive. If we take the inverse of the inverse, that should just return the original element. If we take the inverse of A star B, that's going to be the inverse of each individual element, and then we swap the order around. And the last one, if A star B is A star C, then we can sort of multiply both sides on the left by the inverse of A, and that would get us B is equal to C. Okay, so some useful properties that can be proved from the definitions. And this brings us to the next concept called a field. Again, a field is, we now have 2 binary operations, plus and multiply. Now, definition here is a field is firstly the field including the plus sign, that is an abelian group. Again, an abelian group is a group where it satisfies the 4 definitions, and it also has the commutative law. Okay. And the second condition is if we take this set F and we exclude 0, and we look at the group where we have multiplication, that is also an abelian group. Okay. Now, the reason we exclude 0 is because what we know, like in multiplication, 0 doesn't like have an inverse, because we can't have like 1 divided by 0, that like doesn't exist. So we have to exclude the 0 in this case. All right. And the third thing is the distributive laws. So this is pretty obvious from standard algebra. If we have A times B plus C, well, we just expand it out regularly, A times B plus A times C. And if we do it the other way around, well, we have A plus B times C. That's the same as A times C plus B times C. Okay, so pretty intuitive from your regular algebra. And that brings us on to the next 2 concepts called subgroups and subfields. Back in first year, you would have dealt with like subspaces, and the idea of subgroups and subfields are really like similar. The main thing that you're trying to look at is closure under the operations. Okay. Now here we have a lemma, the subgroup lemma. Okay. Now if G is a group with binary operation star, and consider a, again, non-empty set A, which is a subset of G. Okay. Then we say that the group A is a subgroup of G if and only if these 2 conditions are satisfied. Okay. So the first condition is closure under operation. So if we take any elements A and B of A, then if we take A star B, that's also going to be an element of A. Okay. The second condition is the closure under inverse. So if we take any element in A, the inverse of that element also has to be in A. Okay. And if these 2 conditions are satisfied, then A is a subgroup of G. Okay. And we can denote it again using this less than or equal to sign to denote that A is a subgroup of G. Quick example here. So suppose that G is a group, and for any element little g inside G, we define the set CG is equal to the elements of A inside G, such that if we take GA, it equals to AG. Okay, so that that sort of implies that we have to prove that the commutative law holds, and we have to prove that G is a subgroup of CG is a subgroup of G. Okay. Now, again, for subgroups, we have to prove the two closure conditions, and we have to also make sure that the set is non-empty. Okay, so the first thing is to check that the set is non-empty, and the easiest thing to do is just find an element that exists, usually the identity element. So if we take the identity element E from G, okay, this is also going to be in CG because we know that G times E is equal to E times G. That's going to equal to G, right? So the identity element of G is also inside of CG, and that tells us that CG is going to be non-empty. Okay. All right. Now, next thing is to prove closure. So again, to prove the closure of the operation, we just suppose we take any elements x and y inside CG, and we want to, well, we know that gx is equal to cg and gy is equal to yg. Okay. We want to prove that if we multiply the two elements together, x, y, that is also an element of CG. Okay. So we ultimately want to prove that g of xy is equal to xy of g. Okay. So what we do here is we start off with this equation. We start off with considering the left-hand side of what we want to prove, g times xy. Well, we know that groups follow the second definition. Second definition of a group is that they must be associative. So if we take g times x times y, that's the same as if we bracket the gx first and then multiply by y. Okay. We know that x is inside CG, which means that gx is equal to xg. So this, we can just swap the two elements around, and then in the third line, we can just again group up the last two elements because of associativity, and again we know that gy is equal to yg because we know that y is an element of CG. Yep. And then again, we can group up any two elements. We just group up the first two xy together. And that proves us that g times xy is xy times g. Okay. And that means that xy is an element of CG, and that tells us that CG has closure under operation. Okay. That proves the first closure condition. We also have to prove that that CG is closed under inverse. Okay. So again, suppose that x is any element inside the group, inside the set CG, such that again, this condition holds, g times x is equal to x times g. We're trying to prove that the inverse is also an element of CG, right? So we're trying to prove that if we take g multiplied by x inverse, that equals to x inverse times g. Okay. One thing we can do is we can start with this equation here and multiply the left and the right by x inverse. Okay. So yeah, if we multiply both sides of this equation, gx is equal to xg, by the x inverse on the left and the right, we get that, well, we can group up the last two terms here on the left hand side to get us x times x inverse, and remember that x times x inverse just gets you the identity element E. Okay. And if we multiply E by x inverse g, that just gets us x inverse g, right? Same thing on the right hand side, group up the x inverse and x, and that multiplied together gets us the identity element, which again gets multiplied to g x inverse. Okay. And hence x inverse is inside CG. Right? And hence by the subgroup lemma, we know that CG is non-empty subset, and it's closed under operation and inverse for every element. So hence CG is going to be a subgroup of G. Okay. The next concept is looking at subfields. So subfields, very similar thing as subgroups. except we have two operations to look at in this case. Okay. So let E, such that E is not the zero set, be a non-empty subset of the field F. Okay. Then we say that E is a subfield of F if and only if all of these conditions are satisfied. Okay. So if we take any element inside E, A plus B is also inside E, so that's closure under the addition. The inverse of B is also in E, so I'm saying like the additive inverse, so in this case would be minus B, that is also inside E. If we take A times B, that's also inside of E, so that's going to be closure under multiplication. And if B is non-zero, then the multiplicative inverse of B is also inside E. Okay. So here we're mainly just checking closure, again closure under operation and closure under inverse. Okay. And again we use the notation E is less than or equal to F to denote that E is a subfield of F. Okay. And that brings us on to the next concept called morphisms. Now, we can actually define mappings between two groups using morphisms. So if we have two groups G and H, then the mapping F that maps from G to H is defined as a homomorphism from G to F if the following condition is satisfied. So if we take f of A star B, that's the same as f of A, like circle f of B. Okay, and circle is just the binary operation inside the second, inside the group of H. Okay. If this mapping F is a bijection, so that means it's injective and surjective, then we say that F is an isomorphism. Okay, and the two groups are said to be isomorphic. So, again, from the definitions of the previous slides, these two identities can actually be proved. So, inverse maps to the inverse. So, if we take f of A inverse, that's the same as the inverse of f of A. We can sort of just take the minus 1 outside. Okay, and the identity map also maps to the identity. Okay, so if we take f of E, that is going to equal to E dash, where E dash is the identity in H and E is the identity in G. Okay. Now, quick example here. Suppose G is the set of matrices satisfying this form here, where T is any real number. So T is a group under matrix multiplication. And the question is G with the operation multiply isomorphic to the real numbers with the operation plus? Okay. So the general sort of approach to this question is we want to find a function that maps from one of these groups to the other, and we want to try and see if the function is firstly a homomorphism, and secondly if it's a bijection. Okay. Well, we can consider f that maps from the real numbers to the group G. Okay, where f of t gives the matrix above. So G in this case is the codomain, and we can just represent the function f that maps to this G using just the t variable in this case. Okay. Again, we have to first show that this is a homomorphism. In other words, we have to show that f of s plus t, so we have the plus in the domain, is equal to f of s times f of t, because we have the times in the codomain. Okay. Well, notice that f of s times f of t, we're going to be multiplying two matrices together. Okay. So if we write it out, f of s times f of t is going to be this multiplication here, and if you expand it out, we get this sort of expression here, which turns out to be f of s plus t. Okay? And this is going to tell you that f is a homomorphism between the real numbers and the group G. Okay? And it turns out that f is also a bijection because it's both injective and surjective. Hence, the two groups are isomorphic to each other. Okay. The reason that we have a bijection is because if we take any element inside G, we can just easily represent that from any element inside the domain T, right? Because we let T be any real number. And that makes it really easy to just pick out the element in the domain that maps to that specific element in G. Okay. Alrighty. The kernel of an image, you guys would have met that in like linear transformations. It's very similar sort of concept inside groups. If we have a homomorphism F that maps from G to H, we define the kernel and image as the following. Okay. The kernel of F is the set of all elements in G such that f of G maps to the identity element. Okay. In linear maps, you would have known that the kernel is the set of elements that map to 0. In this case, the set of elements that map to the identity. Image is very similar. So the image of F is a set of elements H such that we have some value G that maps towards that H. Okay, that's every element that has a mapping from the domain. Alright, now quick example here. So suppose we have G be a group with the identity element E, and let H with circle be a group with identity element F. Okay. Let phi be a homomorphism from G to H, and we are trying to show that if G is an element of the group G, and K is in the kernel of phi, then G star K star G inverse is an element of the kernel of phi. Okay. And again, the general approach to proving something is in the kernel of phi is we have to show that phi of this element here maps to the identity element, right? Because that was the definition of a kernel. Because f of G maps to the identity. Okay. Yeah, this is what I just said. To show that phi of this element is equal to the identity element here. Okay. Well, we know that phi is a homomorphism, so if we take phi of a multiplication inside, we can split that out to be phi of G multiplied by phi of K multiplied by phi of G inverse. Okay. So let G be an element of G and K be in the kernel of phi. So that's just looking at the if condition that we're given. Okay. Alright, and here we have a bunch of just manipulation of algebra. Again, the first two lines are using the property of a homomorphism such that we can split the inside multiplication out to the outside, and that gets us phi of G times phi of K times phi of G inverse. We know that K is in the kernel of phi, so that tells us that phi of K maps to the identity element F. Okay? And we know that F multiplied by any element is just going to be that any element because F is the identity in H. Okay? And one of our useful properties was that we know that if we take phi of inverse, that maps to the inverse of phi of G. Right? So inverse maps to inverse, and hence phi of G multiplied by the inverse, well, that just gets us the identity element back in F. Okay, and we have proved that phi of g times k times g inverse. That just gets us f. Alright, and that essentially proves that this element here is inside kernel of phi. Okay, moving on to the next topic, we're going to be looking at vector spaces. Alright. Okay, definition of a vector space. Well, back in first year, you would have had like that long about 10 or 11 conditions. We sort of condensed it down using definition of groups. So in this case, V is in a vector space over the field F if and only if these 6 conditions hold. Okay. A, V with addition is an abelian group. B, scalar multiplication with any alpha is defined. C is this associative law thingy. D is multiplication by 1. E is the distributive law of vectors. And F is the distributive law of scalars. Okay. Usually, we won't, like in exams, they won't really ask you to prove something is a vector space. It's more common they ask you to prove that something is a subspace, which gets us on to the next little theorem. Okay, the subspace theorem. Again, suppose that U is a non-empty subset of the vector space V of F. Okay. Then U is a subspace of V if the following condition is met. Okay. If we have that lambda x plus y is inside U for every single x and y in U and for every lambda inside the scalar F. Okay. So this is just sort of checking your closure under addition and multiplication. And again, we use the notation less than or equal to denote that U is a subspace of V. Okay. Again, why this works? Well, we can confirm that this is closed under scalar multiplication by setting y to equal 0, and that we check that lambda x is inside U, and that checks closure under scalar. Okay. If we set y is 1, sorry, if we set lambda is 1, that would check that x plus y is an element inside U, and that checks us the closure under vector addition. Okay. And lastly is the existence of inverse. Notice if we set lambda to be minus 1 and set y to equal x, we get minus x plus x, and that's an element inside U. Okay, so that checks the existence of inverse. Now, quick example here. So suppose X is a non-empty set, okay, and Y is a subset of X. We want to prove that the set U is a set of all functions f such that f of y is equal to 0 for all y in this set y. Okay, we want to prove that this U is a subspace of the set of all functions f. Well, we can just use the subspace lemma that we had previously. Okay. Now, again, f of x is a vector space, so it contains the 0 function. Remember that every vector space must have that 0 element. In this case, we have the 0 function. We know that for every y inside of this y, if we take the 0 element and we map it, we map y, that just returns 0, right? Which means that this condition is true for the 0 function, and that tells us that the U contains the 0 element, which means that U is non-empty. Okay. And again, to prove that lambda f plus g is inside U, we always suppose that f and g is an element inside U. And one of the conditions inside U was that f of y is equal to 0. Right? So we can assume that f of y is equal to g of y is equal to 0. Okay. And suppose alpha is inside the scalar constant f. Okay. Then if we look at alpha f plus g and we want to evaluate this at y, well, we can easily just expand this out to alpha y plus g of y, and that's going to equal to 0 plus 0, which equal to 0. Right? Because we know our original f and g are inside U, which means that f of y plus g of y is equal to 0. Okay. And hence, by the subspace theorem, we've shown that alpha f plus g is inside U, which means that U is the subspace of f with x. Okay. Now comes on to the next definition of span. Okay. So suppose we have a finite set of vectors S, right? We want to define the span of S as the set of all possible linear combinations of the element of S. Okay. So the span of S is essentially just every single vector that can be written as a linear combination of the vectors inside S. Okay. So what is spanned by the n vectors inside S. Okay. In the case where we have span of S is equal to our vector space V, we say that S spans V, or S is a spanning set for V. Okay. And the next definition is linear independence. So we call a finite set linearly independent if and only if the following equation here, lambda v1 plus lambda v2 plus ... to lambda vn equal to 0, if that implies that all the scalar lambda i's is equal to 0. Okay. So every time you want to prove a set is linearly independent, you always start with the equation, this equation here, and you want to somehow prove that the scalars are equal to 0. Okay. And we call the set linearly dependent otherwise, if this is not true. Okay. Again, linear independence means that we cannot express any of the vectors in a set as a linear combination of the other vectors. Okay. So if you can find a linear combination of one vector in terms of the other vectors, that's going to mean that the set is linearly dependent. Okay. We have a quick example here. So let B be the set of four functions f0, f1, f2, and f3, where f of k from the reals to reals is defined as fkx is equal to e to the minus 2kx. Okay. And you want to consider limits as x goes towards infinity. Prove that B is a linearly independent set. Okay. So again, every question that we have that is getting asked to prove something is linearly independent, we always start off with the equation, in this case alpha f0 plus alpha f1, alpha 1 f1 plus alpha 2 f2 plus alpha 3 f3 is equal to 0. We have to somehow prove that the scalars are equal to 0 as well. Okay. So consider the equation alpha 0 f0 plus alpha 1 f1 plus alpha 2 f2 plus alpha 3 f3 is equal to 0. Now notice that I've used the triple equal sign. Okay, and I've used the triple equal sign to emphasize the fact that this function here has to be 0 for all values of x. Okay, it doesn't mean that it has like a root x such that that function at x is equal to 0. It means that this function here is 0 for every value of x. Okay. And again, in order to prove linear independence, we must show that alpha I values are 0. Okay. Now again, we're starting with this equation, so if we evaluate this at x, we get alpha 0 plus alpha 1 e to the minus 2x, and so on. That's going to equal to 0. Again, emphasizing the equivalence here, we want this equation to be the 0 function itself. Okay. Notice we can take the limits on the left and the right as x approaches infinity. Okay. If we take let's get the pen out. If we take limits as x goes to infinity, this guy here goes to 0, this goes to 0, and this also goes to 0. Okay, which means that a0 is just going to equal to 0. Okay, and if we then multiply both sides of the equation of this equation here by e to the 2x, we know that a0 is already 0, so this term here goes away. Okay, we get this equation here. And again, this equation must be the zero polynomial itself. And we sort of do the same thing where we take the limit of both sides going to infinity. So this guy here goes to 0. This guy here also goes to 0. Okay, which means that a1 is also equal to 0. And you can sort of imagine we keep repeating this process. Multiply the equation again by e to the 2x to get a2 and a3. They're also going to be equal to 0. Okay. And since all of the scalars are equal to 0, that's going to tell you that set B is linearly independent. Okay. Now, naturally, you want to be thinking of a set that would represent a vector space with the minimal number of vectors, okay, such as through spanning sets. Now, suppose we have the set S, which is a subset of the vector space V. The set S is going to be a basis for V if and only if these two conditions hold. Okay, so if we take the set S, it spans V, and that the set is also linearly independent. Okay. Why do we want these two properties? Well, the first one, you can sort of imagine that the set S is representing the entire vector space of V, so every linear combination of the vectors in S, that can represent the entire vector space inside V. Okay, and the linearly independent independence, we say like the vector is pulling its own weight, meaning that like every vector in the set S is playing a role that's building up to a component in some vector V inside V. Okay. All right. Now, standard basis. This is the most simple basis that you guys should all be familiar with. So inside the vector Rn, we have the standard basis E1, E2, all the way to En. And for matrices, we have E11, E12, and all the way to Emn. So in this case, for 2 by 2 matrices, the standard basis would be like 1 0 0 0, 0 1 0 0, 0 0 1 0, and 0 0 0 1. Okay, that's going to be your standard basis for the 2 by 2 matrix. Okay, and a new concept that results from the basis is the dimension. Okay, now consider a vector space V which has a finite basis S. Right? Then we define the size of S to be the dimension of V. Right? So we say the dimension of V is the size of any basis of that vector space V. Okay, so now a lemma. Okay, the following three statements are equivalent. Okay, every time you have this sort of wording that three statements are equivalent, this means that to prove that S is a basis of V, we can prove any one of these statements, and that would like prove the other two as well. Okay, so S is the basis of V. That is equivalent to saying that S is linearly independent and the size of S is equal to the dimension of V. Okay. Or in other words, S is a spanning set and the size of S is equal to the dimension of V. Okay. So in a lot of cases, suppose you know the dimension of some random vector space to be like, for example, like 3, and they've given us a set S and it has 3 elements in it. And if they ask us to prove that that set is a basis for V, right? Because we already know that the size of S is 3 and that equals the dimension of the vector space, we only have to prove that S is either linearly independent or S is a spanning set. Okay, we don't have to prove that it's both. They're both true to prove that it's a basis because of these equivalence. Okay, and usually it's easier to prove that S is linearly independent and the size of S is the dimension of V. Okay. Okay. Again, like example here, consider the degree 2 polynomial vector space P2R. Show that the following set is a basis for the vector space. Okay. Now, dimension of the degree 2 polynomials, that is going to be equal to 3. And notice that inside the set S we have 3 elements as well. Okay. So we know that the dimension is already equal to the size, and from our previous lemma, that tells us that we only need to show that S is linearly independent, and we're done. Okay. Well, again, to show that something is linearly independent, we suppose that lambda 1 times the first element plus lambda 2 times the second element plus lambda 3 plus times the third element is equal to 0. Okay. Now again, notice that I've used the triple equal sign, and that's to denote that this function here is equal to 0 at every value of x. Okay, not just 1 or 2 values of x, but every single value of x, it's equal to 0. Okay. Now, in the next line, I've sort of just rearranged the equation and grouped up the constant term, grouped up the degree 1 term, and grouped up the degree 2 term. Okay. And we want to find the values of lambda such that this is the 0 polynomial. Okay. Well, we can just compare the coefficients on both sides to form the augmented matrix. So notice that we have 2 for lambda 1, 3 for lambda 1, and 0 in the third case. So that would map to 2, 3, 0. We have 0 lambda 2 here, we have 4 lambda 2, and we have minus 1 lambda 2. So that's going to result in 0, 4, minus 1. And we have 1 lambda 3, 0 lambda 3, and 1 lambda 3. Again, that's going to equal to 1, 0, 1. Okay. So we can just solve this using our augmented matrix and just using row reduction. Okay. And when you reduce the matrix, we get this form over here. Okay. And solving this equation, notice that all columns are leading. So if we solve this, we just get lambda 1 that equals lambda 2 equals lambda 3, and that equals to 0. Okay. And hence S is linearly independent, and the dimension equals the size, and hence S is going to be a basis for P2R. Okay. The next concept is the coordinate vectors. So again, suppose we have an ordered basis B with n vectors, and suppose V is a vector inside the vector space V. Okay. Suppose we can write V as a linear combination of these vectors here as alpha 1 V1 plus alpha 2 V2 plus dot 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 alpha n Vn. Okay. Then we say that the vector V with respect to the basis B is just these coefficients out the front, alpha 1, alpha 2 to alpha n, okay, written as a vector like this. And again, this is the coordinate vector of V with respect to B. Okay. And again, the most basic approach to finding the coordinate vectors is just to solve the matrix equation V times alpha is equal to V. Okay. And this is where we have the columns of V are the basis vectors, because essentially we're just solving, we just want to write this vector V in terms of the basis, so we have to try and solve for these alpha 1, alpha 2, and towards alpha n before we can write it in terms of this coordinate vector here. Okay. Now, yeah, other approaches do exist. For example, if you're dealing with polynomials, you can just directly sub in values of x, and that would get you like n different equations, which again you would have to like sort of solve. But if you're smart about it, you can try and make some terms go to 0. For example, if you've been doing like partial fractions, you notice that you can set x to equal some value, and that would remove that term altogether. Okay. Example here, let V be the vector space of all 2x2 real symmetric matrices. Okay. And we let A be this matrix here. Okay. And the question is, find the coordinate vector of A with respect to the following basis here. Okay. Now, the general approach, again, to finding the coordinate vector is we want to write this vector A as a linear combination of these three, sorry, I should be saying matrices. We want to write this matrix A as a linear combination of these three matrices. Okay. A quick sort of side thing here, dimension of symmetric matrices. You guys know that the dimension of 2x2 matrices is 4, but if we look at 2x2 symmetric matrices, the dimension of that is actually just going to be 3. Okay, and the reason is because we can represent the 2x2 symmetric matrices using only 3 elements here, where we have 1 0 0 0, 0 1 1 0, and 0 0 1 0 1. Okay, and this set here is obviously linearly independent, and it obviously spans the set of symmetric matrices. Okay. So again, we want to find the coordinate vector alpha such that we can write A as a linear combination of the basis matrices. Okay. Again, we can just solve this using matrix row reduction. Okay. We're setting alpha of the first matrix plus beta. So alpha 1 of the first matrix plus alpha 2 of the second matrix plus alpha 3 of the third matrix. We can just rewrite this in terms of matrix over here. So if you notice that we have 1, 2, and 4, that gets us onto the first row, 1, 2, and 4. Okay. Minus 2, 1, minus 1. That gets us onto the second row, minus 2, 1, minus 1. Notice that minus 2, 1, and minus 1, that's the exact same. So if we were to write another row, minus 2, 1, minus 1, that would just be redundant because we can just remove that row entirely because it's the same as the second row. Okay? And notice that our last run, 1, 3, and minus 5. That is the bottom row over here. Okay. So if we were to row reduce this, we would get this sort of thing over here, which we can easily solve for alpha 1, alpha 2, and alpha 3. Okay? And again, solving this would result in alpha 3 is 22 on 13, alpha 2 is 29 on 13, and alpha 1 is minus 21, 9 on 13. Okay? And to write the coordinate vector of A with respect to the basis, we just order it such that we write alpha 1 in the first component, alpha 2 in the second component, and alpha 3 in the third component. Okay? The next part here is again only for Math2601, so if you're doing Math2501, you won't need to worry about this little section here, but that's looking at the sums of subspaces. Okay? So the sum of two spaces S plus T, we define this as the set of vectors A plus B, such that A is inside S and B is inside T. Okay? So, and if the intersection between the two spaces S and T, if that's the only, if that's a trivial intersection 0, then we call the sum a direct sum, and we denote it using S, a plus with a circle around T. Okay. Alright. And one of our theorems is that we can find the dimensions of sums of subspaces. Well, we can have dimension of S plus dimension of T. That is going to equal to the dimension of S plus T plus the dimension of the intersection. Okay. One of the, you guys would have known the theorem in probability as well. So if we have probability of A, union B, that's going to be the probability of A plus the probability of B minus the probability of A and B. Okay, so this thing here, it's like really analogous to the probability version that you guys have studied. Okay, so if we just move this guy over to the left hand side, that would be analogous to our dimension equation here. Okay. Alright, now example here, consider these two sets W1 and W2. Okay, it is given that W1 and W2 are both subspaces of the 2x2 matrices. Okay, and part 1 is to write down a basis for W1. Okay, well, one thing you can do, notice if we look at this given matrix over here, right, we can rewrite this as if we split up the x1s and the x2s. Okay, so we have x1, x1, 0, and 3x1. And we add it on with 0, minus x2, x2, and minus x2. Okay. And then if we pull out the x1s out in front and x2s also out in front, we get that a basis is going to be 1, 0, 3 and 0, minus 1, minus 1. Okay. So for part B, we do the same thing. We separate this matrix here to involve y1 in the first matrix, y2 in the second matrix, and y3 in the third matrix. Okay. And hence a basis would be this here. Okay. Part 3 was to find a basis for the intersection of W1 and W2. Okay. Now, to solve for the intersection, okay, we need to find a matrix X that is both in W1 and W2. Okay. And hence we must find a matrix that satisfies this equation here. Now, if we equate the corresponding entries, x1 equals y1, minus x2 is y2, minus y3, and etc., we get this expression here. Okay. And we essentially have to solve this equation. Okay. Now, if you sub equation 1 to equation 3, right? So let's get it on ink. So equation 1 to equation 3, we get that x1 plus x2 is equal to x1 plus y3. Cancel these guys out, we get x2 is y3. Okay, and this result here, we can again sub it into equation 2. Okay, and that would get us y2 is going to equal to 0. Okay, and again, this equation here, we sub it to equation 4, and that would get us that 3x1 minus x2 is equal to y1. But we know that y1 is equal to x1 from this first equation here, and hence that gets us 2x1 is equal to x2. Okay. And hence x must be in this form here, where we have x1 minus x2, x1 plus x2, and 3x1 minus x2. Okay. And again, we can replace x2 with minus 2x1. That is this last condition here. And again, replace x2 with 2x1 to get us 3x1 in the bottom left here. And replace this last x2 with, again, 2x1. And that gets us x1 in the bottom right. Okay. And again, that means this here, we can rewrite this as x1 multiplied by 1 minus 2, 3, 1. Okay. So the intersection of W1 and W2 is spanned by this matrix here. Okay. It's going to be the span of that matrix. And hence a basis is just going to be 1, minus 2, 3, and 1. Okay. Now for the last part, find a basis for W1 plus W2, which includes your basis from part 2. So it includes the basis from W2. Okay. Now, to find the dimension of sums, we want to use this property here, where we have dimension of W1 plus dimension of W2 is dimension of the sum plus the dimension of their intersection. Okay. Rearranging this gets us dimension of W1 plus dimension of W2 minus dimension of their intersection. And again, to find their dimensions, we just want to take the size of their basis. Okay. So notice that a basis here was just size 1. Basis here was size 2. Basis for this one was size 3. Okay. So we get 2 plus 3 minus 1. Okay. And because we have the dimension of the sum is equal to 4, we know that the dimension of the 2 by 2 matrices is equal to 4, right? And that means that W1 plus W2, that must span the entire space of the 2 by 2 matrices. Okay. So to find the fourth element of the basis, we can just extend the basis that we found in part 2. Okay. So we just extend this basis, and the easiest way to extend a basis is to consider the standard basis of M22R. Okay, so consider these elements here. 1, 0, 1, 0, 0, and 0, 1, 0, 0. Okay, we have to find that which one of these elements is linearly independent of the other 3 elements. Okay, so which one of these elements here is linearly independent of these 3 elements? Okay, and you can do the nitty-gritty algebra, but upon inspection, you're going to get that this element here is going to be 0, 0, 0, 1, and that's the element that's going to be linearly independent of the other 3 elements. Okay. And if you add this to the basis in part 2, so again, extend this out, 0, 0, 0, 1. This set here is going to be the span of W1 plus W2. Okay. And that brings us on to the next chapter on linear transformations, and I am going to now be passing over to Lachlan, who's going to be taking the rest of today's part. Okay.
All right. Hello. I think we should be live now. Just give me one moment to sort some things out. All right, perfect. So, let's get back into it now. So, we're starting off with topic 3, which is linear transformations. So, thank you to Fred for presenting the previous two parts. So to begin, we're just looking at the definition of a linear transformation. So a linear transformation is a function between vector spaces. So in this case, between two vector spaces, V and W. Now it is linear if it satisfies these two conditions. So if we add two vectors inside the function, then we add the two function values, and same with a scalar multiplication. Now, in order to test whether a given function is a linear transformation or a linear map, what we can do is just consider, okay, where does the vector x plus lambda y get mapped to? If it gets mapped to t of x plus lambda t of y, then we're dealing with the linear transformation. So this sort of combines these two above conditions into one. Now, I guess a sort of warm-up example for us would be to test whether this function below is linear, so prove this is linear. Now, in order to do that, all we have to do is consider two vectors, x and y, that are part of our domain, okay? And so we'll say, okay, x equals x1, x2, and y equals y1, y2. And then the question is, if lambda is a real number, where is t of x plus lambda y mapped to? What does that equal to? And more importantly, I guess, does it equal t of x plus lambda t of y? So you can see that if we actually plug these values in, when we get to this step, now we are going to apply the actual linear transformation here. So in this case, you can see that the I guess the linear transformation here is taking x1, x2 to these values here. So if we actually plug that in, you can see that we can actually kind of separate out this new vector. So we can bring all the x terms to one side, all the y terms to the other side. And if we bring all the y terms to the other side, you can see that we can actually factor a factor, I guess, of lambda out to the front. And then we're left with t of x plus lambda t of y. All right, so now looking at some definitions here. You saw Fred talk earlier about kernel and image. Now we can extend the idea of kernel and image to a linear transformation. Okay, so in terms of linear transformations, right, the kernel is a set of all things that make t zero. So in other words, the set of all zeros, or all the values such that t of x equals the zero vector. Now the image is a set of all possible values t can take, okay, which is sort of the range of the function. So the definition of these two sets formally are these here. So the kernel, again, is a set of all vectors which map to zero, and the image is where all of these vectors in the domain get mapped to, okay? Now we can prove that the kernel of T and the image of T themselves are vector spaces under the field F. Now, in terms of these vector spaces, because they are vector spaces, we can, determine basis bases for them and their dimensions, right? So some special definitions we have here are the dimensions of the kernel and the image. So the dimension of the kernel of T is the nullity, and the dimension of the image of T is the rank. Okay, and the reason why these are useful to look at, well, one particular reason is the rank nullity theorem. So if we add the rank of T and the nullity of T, we always get the dimension of the vector space V, which is the domain of T. Okay, so moving on to another useful property of rank and nullity. So in terms of rank and nullity, they help us determine whether a certain linear transformation is invertible. Okay, so in particular, these three statements are all equivalent. Okay, the nullity of T equals 0. So this is equivalent also to saying the kernel of T is only the 0 vector. Okay, um, and then this one, the second one, the rank of T equals the dimension of V equals n. So the reason why that's equivalent is by the rank nullity theorem. So remember the rank of T plus the nullity of T must equal the dimension of V. So if nullity of T equals 0, then clearly rank of T equals dimension of V. And the last one is T is invertible. So if we have any of these two conditions, so the nullity of T equals 0 or the rank of T is n, which is also referred to as full rank, then T is invertible. All right, so let's move on to an example of rank and nullity. So this is a question from the 2020 past paper. So this question says, let S be a P by P real matrix that is fixed, and define a linear map T on the vector space of P by P real matrices by T of A equals S times A. So in other words, basically I take some matrix, some P by P matrix, and the linear transformation here is just multiplying it by some fixed matrix S. Now show that rank of T equals P squared if and only if S is invertible. So first thing we can do is break down this question, okay? So we can kind of see that we're dealing with the vector space of P by P real matrices. Now this has dimension equal to P squared, okay? That's because, just like the dimension of 2 by 2 real matrices is 4, the dimension of P by P real matrices will be P squared, okay? So in other words, saying that rank of T equals P squared is equivalent to saying it has full rank, okay? And so we want to prove that it has full rank if and only if S is an invertible matrix, okay? And so keep in mind this is an if and only if, so we need to prove both the forward and the reverse direction, right? So we'll start off by proving in the forward direction. So in the forward direction, we'll say, suppose that the rank of T does equal P squared. Now we need to prove S is invertible. So clearly, if the rank of T equals P squared, that's saying that for any, I guess, for any matrix, we'll call it A. So not A, we'll call it B, is an element of P by P real matrices, sorry. Then it must be true that there exists some A such that T of A equals B. So the reason why that is because we're saying that the rank of T equals P squared. So that means that any element of our vector space is in the image of T. So in other words, there has to be some vector that I put into the linear map to get B out, okay? So if that's the case, right, then the identity matrix, right? The identity matrix is certainly part of the image of T, okay? If that's the case, so we're saying that P by P identity matrix is in the image of T, okay? Then there needs to be some matrix Q such that T of Q equals the identity matrix, right? Because the identity matrix is in the image of T. Right, so if that's the case, right, then we can say that, okay, clearly, because T of A equals SA, then T of Q equals SQ, which equals our identity matrix. Now you can see that what we have here is essentially saying that, S times Q equals the identity matrix. So Q must be S inverse, right? In other words, saying that S inverse exists and therefore S is invertible. So we get S is invertible. So that's our first direction of the proof complete. Okay, now we need to look at the other direction. So the other direction here is if S is invertible, then rank of T equals P squared. So let's suppose that S is invertible. So if S is invertible, then nullity of T must equal 0. Okay? And that's from our previous theorem, okay? So our previous theorem said that if S is, or some linear map is invertible, then its nullity is 0, okay? So, essentially we just need to prove that, let's see. So we need to prove that, I guess, the kernel of T is 0, which proves that the nullity of T is 0, okay? So, it's sort of just a matter of finding the kernel of T. So in order to find the kernel of T, okay, we need to find the set of all vectors that map to 0, okay? So to do that, one way of doing that is to say, okay, let's suppose that T of A equals 0, okay? So that's saying that SA equals 0. Now, clearly S is invertible, right? So, if that's the case, then the only way for SA to equal 0 is if A equals 0, right? So now, if A equals 0, then clearly the only element in the kernel of T is 0, right? Because you can say we just assumed an arbitrary element was in the kernel. And then we proved that it equals 0, so that means the kernel must be 0. So that's saying the kernel of T is 0, and hence nullity of T is 0, implying by the rank nullity theorem. So by rank nullity theorem, the rank of T must equal the dimension of the original vector space, which is P squared. Okay, so just to quickly outline the proof, what we did was say, okay, S is invertible. Now we need to prove that rank of T equals P squared. Another way of doing that is to prove that the nullity of T equals 0, because clearly, if that's the case, then by the rank nullity theorem, the rank of T equals P squared. And to do that, we use the fact that S was invertible. So now, we're essentially done with this question. So we proved the reverse direction, and therefore rank of T equals P squared if and only if S is invertible. All right. So now let's go on to a very important idea. Very important idea in our linear transformations, and that is the matrix representation of linear maps. So the key idea here is that every linear map, okay, is represented or can be represented by matrix multiplication. So you could take some arbitrary linear map on some arbitrary vector space, okay? So let's say we had, for example, the vector space of polynomials, right? So like the set of all like quadratic polynomials, for example, right? Now, you could define some linear transformation on this. So an example would be differentiation. Now this theorem tells us that we can represent this linear map by matrix multiplication. In order to do that, essentially all we need to do is find coordinate vectors. So remember from Fred's previous topic that any vector in a vector space we can represent with respect to some basis by finding its coordinates. For example, you could say, okay, 1x x squared, this is our basis for quadratic polynomials, and this would be 1 0 0, that would be 0 1 0, that would be 0 0 1. Okay, and now essentially any quadratic we can represent in terms of coordinate vectors, and then any linear transformation we can represent by multiplying by some matrix with respect to that basis. So we take any vector in the with respect to those coordinates and just multiply it by a matrix. So in terms of the actual statement here, right? Suppose that some linear transformation from V to W is linear with basis B and for the domain and C for the codomain. Then there exists a unique matrix A such that if we find where V goes to under the linear map, so T of V, and express it with respect to the basis C in the codomain, that is just equal to some matrix A times the coordinate vector of V with respect to B in the domain, okay? So we take V in the domain, and then we find its coordinates with some basis, and then we multiply it by the matrix A, and then what we'll get is the result if we just found the linear transformation and then express it with respect to the basis C, okay? So if we know the coordinate vector of V with respect to basis B, then we can use the matrix A to find T of V with respect to the basis C in the codomain, okay? So essentially, I guess one way of writing this matrix A is as this. So we have T, B, C, okay? And this is telling us that we have the linear transformation B, okay, written with respect to these bases. So C in the codomain and B in the domain. So now an important question is, how do I find this matrix representation? So it's actually fairly straightforward. Essentially, first thing we need to do is actually find our bases in the domain and codomain. So we need to write down our bases B and C. And so if P is the dimension of our domain V, we can say that our basis is V1 up to Vp. Okay. Now, in order to find the matrix A, essentially all we need to do is ask ourselves, okay, where does V1 go under the linear transformation? Okay, so we take the first basis vector and then we map it under T. Okay, so if we map it under T, what we're going to get is some vector. It's going to be T of V1, right? And now in order to find the matrix, right, remember this is now in our codomain, okay? So we need to express it with respect to the basis C, okay? All right. And then what we do is repeat that for every single vector in our basis B, and our matrix will just be all of these vectors, okay? So all the basis vectors written with respect to the basis C in the codomain. And that's just our matrix, okay? So this is a fairly straightforward process if our bases are the standard bases B and C. However, for more complicated bases, it's a bit more difficult. So the general approach is this, okay? What we're going to do is sort of convert to standard bases and convert back. So a very key idea here is that taking coordinates. So for example, if I have a vector and then I express it with respect to a basis B, okay, itself is a linear transformation. This is a linear transformation. Now, if this is a linear transformation, it can be represented by matrix multiplication, okay? So there will be some matrix, right, that um, is equivalent to taking coordinates, okay? And I'll illustrate what I mean, okay? So let's say I have some basis in, I guess, R2, and I'll call it 2, 1, and -3, 5, for example, okay? Now, clearly this is a basis. It's not our standard basis. Our standard basis would just be 1, 0, 0, 1, okay? Now the question is, how can I transform vectors with respect to the basis B to vectors with respect to the basis S? Now, a very key idea here is that if I transform one vector with respect to the basis B to another vector with respect to the basis S, I'm not actually changing the vector, I'm only changing its representation. So it's a sort of identity map, okay? Because I'm not actually changing the vector. So to do that, consider the fact that 2, 1 written with respect to my basis B is just 1, 0, and -3, 5 written with respect to my basis B is just 0, 1, right? So now you can see that the matrix 2, 1, -3, 5 is actually a matrix that will convert my basis B to the standard basis. And now to kind of illustrate that idea, if I multiply it by 1, 0, which is, you know, 2, which is the first vector in my basis B, what I'm going to get out is 2, 1, which is exactly its representation with respect to the standard basis. Okay, so you can kind of see that writing down a matrix that converts from some basis to the standard basis is just a matter of writing down the basis vectors written with respect to the standard basis. So in this case, 2, 1, -3, 5. I'll illustrate this in another example very soon. And so I guess the point here is that in order to find the representation of some arbitrary linear map with respect to some arbitrary bases, what we're going to do is use this very easy approach to convert to standard bases to sort of write out the whole idea. So essentially the main formula here would be this equation here. And it has a very, I think in my opinion, a fairly straightforward idea. And the idea here is that I want to find the matrix of some linear transformation with respect to B in the domain and C in the codomain. Now this will be a very annoying process normally using this previous method that I illustrated, because what we're going to have to do is find a bunch of vectors, find their linear transformation, and then express them in new coordinates with respect to C. Okay? But we can do it this way instead. And this way is sort of, first, what we're going to do is take a vector expressed with respect to B, expressed with respect to the basis B. So we'll have vector, so we'll call it V, and then we'll express it with respect to the basis B. And then what we're going to do is map it so it gets written with respect to the standard basis. Standard basis. Okay? And in order to do that, all we need to do is multiply by this matrix here. Okay? So this matrix here will map my vector with respect to the basis B to the vector V with respect to the standard basis. Okay? And now I have a vector with respect to the standard basis. I'm going to map it to T of V with respect to the standard basis in the codomain. Okay? So just keep in mind, if we have a linear transformation, for example, from r squared to r cubed, okay, what's going to happen is we're going to have two different standard bases in the domain and codomain, but they'll both be very straightforward. So essentially we find V with respect to standard basis, and then we find T of V with respect to standard basis in the codomain. And then once I've got T of V written with respect to the standard basis in the codomain, I now want to write T of V with respect to the basis in the basis C in the codomain, okay? Because the whole idea was I wanted to find the linear transformation with respect to B and C, okay? So I'm sort of going from B to standard basis, going from standard basis, apply the linear transformation, and then go from that to the basis C, okay? And this whole process is represented using this equation here. So we'll jump into an example to make it clear. So consider the linear transformation defined by this. Okay, let the basis B be this basis here, and C be this basis. Now you can see the issue is that I have some linear transformation and I have these annoying bases to work with. Okay, so what we're going to do is apply the previous method. So in order to do this, essentially what I need to do is, well, first find all of these matrices. So I need to find the matrix that converts basis B to standard basis, and I need to find the matrix that converts basis C to standard basis, and then I need to find the linear transformation with respect to my standard bases. So I guess the first thing we can do is find find the matrices that convert my coordinates. Okay, so in order to do that, we'll denote this as the matrix that converts basis B to my standard basis in the domain. Okay, and my standard basis in the domain is 1, 0, 0, 1. Okay, and this matrix here will be my my matrix that converts basis C, okay, to my standard basis in the codomain, which is just 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so you can see, how do we actually find these matrices? Well, you can see that it's just a matter of chucking my, like you see we have these representations of them. We have the basis B and the basis C. In terms of writing out these matrices, it's just going to be turning these column vectors into a matrix where the columns are the vectors themselves, right? So just sort of reading off, okay, I have 1, 0, 1 as my first vector, so the first column will be 1, 0, 1. And my second vector is 1, 1, 0, so my second column will be 1, 1, 0, and so forth, right? And now these will be matrices that convert basis B to standard basis, basis C to standard basis. Now I need to find the matrix that represents this linear transformation, okay? Now in order to do that, it's fairly straightforward because I'm only doing it with respect to the standard basis. And now it just becomes a matter of saying, okay, where does the first basis vector go and where does the second basis vector go? So t of 1, 0 will be, okay, if I actually figure it out, it should be 1 plus 0, 1 minus 0, 3 times 1. And what I'll get is 1, 1, 3. And then t of 0, 1 will be, very similarly, it should just be 1, negative 1, 3. Oh, so 1, negative 1, 0. Okay, so my matrix representing the linear map will be 1, 1, 3, 1, negative 1, 0. And now in order to find the representation with respect to C and B, it's just going to be, okay, first thing I need to do is convert my basis B to the standard basis. Okay, so basis B to the standard basis. And then once I'm in the standard basis, I'm going to apply the linear transformation. So I go from my standard basis 1 to my standard basis 2. And now what I need to do is go the other way around. So go from my standard basis 2 to the basis C. And in order to do that, we have to find the inverse of this matrix here. And now, in order to find the linear map, I guess we just have to multiply these all together. So unfortunately, to find the inverse of a 3 by 3 matrix, we'll have to, it's a sort of annoying process, but we've learnt it all in first year, so I'll skip the actual calculation. We'll take it to be this matrix here. And then all we have to do is take these three matrices and multiply them together. And then this will be our result. So we're going to move on to invariant transformations, which is a Math 2601 topic only. So an invariant subspace is one that sort of doesn't change under the linear map. So in particular, we can say that if X is some subspace, okay, it's an invariant subspace if, so it's invariant if T of X, so the image of X under the linear transformation, itself is a subspace of the original X, okay? And this only works if we have a linear transformation from V to V. So in other words, applying T to any vector in an invariant subspace results back in a vector that's still within that subspace X, okay? So we'll move on to an example. So let T be a linear transformation from R cubed to R cubed, okay? And this is our linear map. It's represented by matrix multiplication with this particular matrix. Now define a subspace W by W equals the span of these two vectors. Prove that W is invariant under T. So to prove it is invariant, what we need to do is show that T of W is a subspace of W, okay? So we already know that W is a subspace, so all we really need to do is show that T of W is a subset of W, okay? Because T of W is also a subspace. So essentially we need to show that any vector that's in T of W must be in W, okay? So keep in mind that any vector in W, okay, because it's the span of those two vectors will be some lambda times 0, 1, -1, plus some mu times 2, 1, -1. Okay, so if that's the case, then T of we'll call it a vector y. Okay, now T of we'll call it x. Sorry, T of x will just equal the matrix A multiplied here, which is just a matter of multiplying each component vector. So we get this. Oops. Okay, so essentially, all we need to do is find, okay, what are the vectors A multiplied by 0, 1, -1, and A multiplied by 2, 1, -1. Now, applying the actual matrix vector multiplication, we'll get these two vectors. So now you can see that any vector that's an element of T of W is part of the span of -4, -1, 1, and -6, 3, -3. Okay, so all we have to do is show that every vector that's in this span is also a vector of that's a part of W. Okay, and in order to do that, what we kind of have to do is just show that these two vectors, so this vector and this vector, themselves are in W. Because if they're both in W, then their span must be also part of W, because W is a closed subspace, okay? So it's just a matter of finding these two vectors as part of the span of W, okay? And in order to do that, for example, with the first vector, keep in mind that W is the span 0, 1, -1, so 2, 1, -1. So all we really need to do is sort of solve this system and find, okay, what are the values of lambda and mu such that this is true, okay? And likewise for our second vector, which is -6, 3, -3. And if we actually do that, then we'll see that those vectors are a linear combination of vectors of W, which means that these vectors must be in W, and so therefore y is in W, and therefore T of W is a subspace of W, and therefore W is an invariant subspace. So moving on to another key idea, this is similarity. So similarity, the idea behind similarity is that we can represent different linear maps, the same linear map, okay, with respect to different bases, okay. So if we saw earlier, right, in this question here, that we had some matrix, we had some linear transformation, right? So we had a linear transformation represented by this. Now we could represent this linear transformation with respect to the standard bases. So we got this. But we could also express it with respect to the bases B and C, in which case we got this. So we have the same linear map, but it has two matrix representations. So you can see that different matrices can represent the same linear map, but written with respect to different bases. So the idea here is similarity, or the idea behind similarity is that two matrices are similar if they represent the same linear map with respect to different bases. So in order to do that, we can say that they are similar if there exists an invertible matrix P such that B equals P inverse AP. And the reason why is because this matrix P allows us to convert bases. So this is saying that they represent the same linear map with respect to different bases, and the actual matrix P is there to convert between bases, okay? And if you see how it's a P inverse AP, that's it's very similar to this equation here, okay? In order to represent a linear map with respect to two bases, okay? Well, I guess in this case, four different bases, right? One in the codomain domain, and another one in the domain and codomain. We sort of needed to sandwich it between these two different matrices, okay? Okay, so in terms of similarity, in order to show that two matrices, for example, weren't similar, we can look at some things called similarity invariants, which hold whenever A and B are similar. So for all similar matrices A and B, their rank must be equal, the nullity must be equal, the trace must be equal, and the determinant must be equal. So remember that the trace is just the sum of the diagonal elements. Now, if all of these properties hold, it doesn't necessarily mean that it's similar, because there may be similar matrices there may be matrices that have all of these properties the same but aren't similar. Okay, so these ones are only really useful for proving that they're not similar. Okay, so to prove that these two matrices are not similar, all we have to do is check that one of their similarity invariants is not the same. So check similarity invariants. So we can check the trace. So we add the diagonal components, we get the same value. So now we can check determinant. So we'll skip the actual calculation of the determinant for now, but you can see that they do have different determinants. So because one of their similarity invariants is not the same, then they can't be similar. Okay, so these two matrices are not similar. All right, so we're going to move on to the next topic, which is inner product spaces. So the definition of an inner product is some function that takes two vectors inside a vector space and outputs a number in the field f with the following properties. Okay, so if you look at these properties, we can kind of see that the inner product is sort of a generalization of the dot product, the usual dot product. Okay, and in order to prove something is an inner product or valid inner product, you'd have to prove all of these four properties hold. Now, in terms of inner products, right, we can sort of extend the ideas that we know for the normal dot product to this general inner product. So one idea is perpendicular, whether two vectors are perpendicular. We extend that to the idea of orthogonality, okay? So two vectors are orthogonal if their inner product is 0, okay? Now, in terms of this definition, orthonormal, a set of vectors is orthonormal if each vector is mutually orthogonal, okay? And their lengths are all 1, okay? So if you look at this here, this is saying that, okay, if I have the same vector, vi, I'm going to get 1 out, okay? So the inner product with the vector vi in itself is 1, okay? But if I take any two different vectors, then I should get 0 because they need to be mutually orthogonal, okay? So they're orthonormal if all the vectors have length 1 and are all mutually orthogonal. So now we introduce the idea of a projection. So the projection of x onto y is given by this formula, this expression, okay? Now, keep in mind that x minus the projection of x onto y is orthogonal to y. And that's very useful for us when we go into the Gram-Schmidt process. So the Gram-Schmidt process is a way of taking a set of vectors and turning them into an orthonormal set of vectors. Now, the reason why this is useful is given an inner product space. So an inner product space is a vector space equipped with an inner product. We can show that it has an orthonormal basis, okay? So keep in mind that, there can be any there can be a bunch of different bases for a vector space, but we can also any inner product space will have an orthonormal basis. So that's a set of vectors that is a basis, but it's also orthonormal. Now, so if we wanted to actually find an orthonormal basis, to do that we need to use the Gram-Schmidt process on any given basis. Okay. So the Gram-Schmidt process is this: you take one vector, you take the set of vectors v1 up to vn. Okay. And our goal is to express them first as an orthogonal basis, okay, where all the vectors are mutually orthogonal. And we'll call that w1 up to wn. So the first w1 is just going to be the original v1. Now for v2, we need to take v2 minus the projection of v2 onto w1. So keep in mind from our definition of projection that x minus the projection of x onto y is orthogonal to y, okay? So this will be orthogonal to w1, all right? And this will be orthogonal to w1 and w2, okay? And then we can keep going and going. And then what we'll have is, if we do this major process, we'll have a set of orthogonal vectors. Now, in order to make an orthonormal basis, all we need to do is rescale each vector in our basis so that it has length 1, okay? So that will give us an orthonormal basis. Okay. So we'll have an example here. So let W be a subspace of R4 that is spanned by the following vectors: v1, v2, v3. Find an orthonormal basis for W. Okay, under the regular dot product. So that will be our inner product. So in order to do that, we need to do the Gram-Schmidt process on v1, v2, and v3. So w1. Okay, remember w1 will be our first orthogonal vector. It's just v1, and we'll say that's equal to this vector here. Now w2, in order to find w2, what we're going to need to do is take v2, so this vector here, and then subtract the projection of v2 onto w1. So remember the projection is given by this expression here, okay? And so if we actually just calculate this, keep in mind that this inner product is the regular dot product. So for example, this inner product would actually just equal 1 times 0 minus 2, okay, plus 0, 0. So we just get negative 2 out, okay? And also this denominator will be the square root of 2 squared. So we'll have just this here. And our second vector will be 1, 1, 1, 0 transpose. And now to find the third vector, what we're going to need to do is take v3 minus the projection of v3 onto w1 minus the projection of v3 onto w2. And so we'll do a bunch of projections, and then what we'll finally get is 0, 0, 0, 1 transpose. Okay, so our orthogonal basis will be these three vectors. Now to find our orthonormal basis, we're going to have to divide by the length of each vector. Okay, so for example, the length of vector 1 is 1 on root 2, so we'll divide by root 2, and so forth. All right, now we'll look at this idea of projections onto subspaces. So first we need to look at this definition, the orthogonal complement. So given some subspace W, the orthogonal complement, is the set of all vectors which are orthogonal to every vector in W. So if I take a vector in W perpendicular, which is the orthogonal complement, every vector must be orthogonal to every vector in W, okay? So now a major theorem here is that given any subspace W, okay, the direct sum of W and the orthogonal complement of W will equal the original vector space, okay? And what that tells us is that any vector x in V can be expressed as x equals a plus b, where a is in W and b is in W complement, okay? And so these vectors will be perpendicular, orthogonal, sorry. All right, and now in terms of this, we call A the projection of x onto W, and we'll call B the projection of x onto W complement, okay? And so our useful fact here is that x minus the projection of x onto W is an element of the orthogonal complement, okay? So we'll look at a question here. So let W equal the span of V1 and V2, where V1 and V2 are given by these vectors. Find the projection of X onto W with the usual dot product on R4. So in order to do that, we'll say, okay, Y will equal the projection of X onto W. Okay? Then if that's the case, right, Y will equal a linear combination of V1 and V2, right? Because W is the span of those two vectors, okay? Now we'll also require that X minus Y is part of the orthogonal complement of W, okay? So now we kind of just need to find, we need to make sure that every X minus Y is orthogonal to both V1 and V2, okay? So we'll say, all right, so clearly if that's the case, then X minus Y must be orthogonal to V1, so that dot product equals 0, and X minus Y will also need to be orthogonal to V2, so that dot product will equal 0. And if you actually do that, so we're saying Y equals lambda V1 plus mu V2, we can find these dot products, and what we'll get is actually two linear equations in two variables. And so we can actually solve this to get the values of lambda and mu as required. And so this will be our vector, or our orthogonal projection, or projection of X onto W. So a useful, I guess a useful consequence is QR factorization. So a QR factorization is given, if we're given some full rank P by Q matrix A, okay, then we can factorize it into Q times R, where Q is a P by Q orthogonal matrix, and R is an invertible Q by Q upper triangular matrix. So this factorization looks like this, okay? And in order to actually do it, right, in order to actually find it, our method will be to take the columns of, we'll call it A has columns A1, A2, all the way up to A Q, right? And then from here, what we're going to do is apply the Gram-Schmidt process to A1, A2, up to AQ. And our new orthonormal basis, or orthonormal version of A1 up to AQ, sorry, will be Q1, Q2 up to QQ. Okay, and now that will form our Q matrix. Form our Q matrix, and then our R matrix will be formed by all of these numbers that we get from performing the Gram-Schmidt process. So we'll go through an example. So let's find a QR factorization of B equals 1, 1, and so forth, right? So in order to do that, what we're going to have to do is call that V1 and V2 and apply Gram-Schmidt to V1 and V2. So we'll say, okay, W1 equals 1, 1, 1, 1 transpose, and W2 will equal the second column, which is 1, 2, 3, 1, 2, 4, 5, minus the projection of A2 onto W1. And again, that projection will be done using the usual dot product. And then what we'll get is this vector as a result outwards. And so that's telling us that Q1 will equal the normalized version of W1. So normalized means we divide by its length, so it's unit length. And same for Q2. And so if that's the case, our Q matrix will be 1 half, 1 half, 1 half, 1 half, and then negative 2 on root 10, negative 1 on root 10, 1 on root 10, and then 2 on root 10. Okay? And now in order to find our R matrix, remember our R matrix looks like this, right? So we just need to put the lengths of W1, W2, and put these dot products in there, which we all already found by actually computing or by applying the Gram-Schmidt process. So we can see that Q1 dot product A2 will equal 6, okay? And so our R vector will just be 2 root 10, 6, okay? And 0 there. So you can see that these, where the question is, I guess, where are these diagonal elements coming from? They're just the lengths of our vectors, V1 and W1 and W2. And so that's our QR factorization done. So move on to an idea that's only in Math2601, and that is the adjoint. So the adjoint of a linear map is T star, okay, which is sort of a generalization of the idea of the transpose of a matrix, okay? Now, in terms of its actual definition, it's saying the adjoint is a matrix T star such that the inner product between W and T of V is equal to the inner product of T star of W and V, okay? And so we have some properties of adjoints. If we take the sum of two linear maps, that will be the sum of the adjoints, okay? We can pull the um, scalar out of the adjoint by conjugating it. If we adjoint twice, then we get the original matrix or the original linear map. And you can see that if we have a composition, then we sort of reverse the order of the adjoints. So you can see that this is sort of an extension of the idea of the properties we already knew of the transpose. Now, an important notion is that I guess for real matrices, the adjoint will be the transpose, but for complex matrices, the adjoint is going to be the conjugate transpose. So we take all the conjugate of every element and then we transpose it. Okay, so it's very important we don't forget that. It's a conjugate transpose for complex matrices. So we'll look at an example here, okay? So consider these two vector spaces equipped with these inner products, okay? So I guess the inner product of P and Q is defined by this integral. And this is on the set of quadratic polynomials. And then on, I guess, the real numbers, our inner product is just 4u times v. So define a linear map from v to w by t of p equals p of -1. Find a formula for t star of v. So in order to do that, all we need to do is find the linear map t star such that u, the inner product between u and t of p, equals the inner product between t star of u and p. Okay? For all u is real and p is in our quadratic polynomials. So, in order to do that, let's consider this inner product. So we'll find the inner product between u and t of p. So keep in mind that in this case, right, we're saying u is a real number and p is just a polynomial. So t of p, first thing we need to do is find t of p. Now in order to do that, we'll have to say, okay, p of t is, sorry, p of t is just some arbitrary quadratic polynomial, okay? And furthermore, keep in mind that t star of u, okay, will be another arbitrary quadratic polynomial, okay? We'll call it q0 plus q1t plus q2 of t squared. And the reason why that is because you can see that on the left, we have the inner product on R, and on the right, we have the inner product on P2 of real numbers, okay? So I guess T star of u will be a quadratic polynomial, and it's in our best interest to write it in this form, okay? And similarly, we'll write P in this form. And so now we actually have to find these two inner products. So we'll find the inner product here, and we'll find the inner product here, and we'll actually just equate them and see what we can do. So the inner product between u and t of p, okay, will be this, okay? 4 times u times p of -1, okay? The reason why that is because remember t of p equals p of -1. Now p of -1 will just equal this because we're sort of subbing in t equals -1 into that equation. Now we'll find the other inner product. So t star of u and p will be this integral between these two polynomials. And so we can expand everything out and use the given identity, and we'll get that this is our inner product, okay? And so essentially all we need to do is equate these two inner products and sort of solve by equating coefficients. So the idea is that we need to find Q0, Q1, and Q2 in terms of U so that we are able to find an expression for the linear map T star, okay? Because remember, that's the goal of this question, to find what is T star. So I guess doing that, what we'll say is sort of first thing we're doing, sorry, is grouping this original this inner product here in terms of the coefficients P0, P1, and P2. And the reason why that is so we can equate coefficients of P0, P1, and P2. And so if we actually equate, remember that U T of P was equal to 4U P0 minus P1 plus P2. Okay, so what we're saying is that, okay, these must be equal. These two must be equal, right? So if that's the case, then 2Q0 plus 2/3 Q2 will equal 4U. And 2/3 Q1 will equal negative 4U. And so forth, right? So what we'll get is these equations, these three equations, and our goal now is to actually just solve for Q0, Q1, and Q2. Sorry, Q0, Q1, and yeah, Q2. So if we actually just do this, we'll find that Q1 equals negative 6U, Q2 equals 15U, and also that Q0 equals negative 3U. Okay? So what that's sort of telling you, sorry, is that T star of U will equal negative 6U, negative 3U plus 15, negative 6U, negative 6UT plus 15UT squared, okay? And so given a real number U, we're sort of mapping U to this polynomial. And so what that's telling you is that the linear map T star of U will just be this, okay? So given any real number U, that's our linear map, and that will be T star. So the adjoint of our linear map will be given by this linear map, okay? And so that's how we find adjoints in a more general scenario. It's sort of equating those inner products and then solving for the actual linear map T star. So another idea in Math2601 is certain types of linear maps, okay, that have special adjoints. So the main ones are unitary, which is when the adjoint equals the inverse. Hermitian, also known as self-adjoint, when the adjoint equals itself. And an isometry is when, so it should be this, okay, is when the norm is sort of unchanged under the linear map, okay? Okay, so again, the idea here is that the adjoint of a complex matrix will be the conjugate transpose, okay? Now, we also have the linear map is an isometry if and only if it is a unitary, okay? So these will be useful in this question. So let T be a linear map from these two complex vector spaces defined by T of WZ equals 2Z minus W, defined with the standard inner product. Is T isometric? Is it Hermitian? So to do that, the sort of best way to do it would be to find, I guess, the matrix representation first. So to check whether it's isometric, first thing we can check is whether it's unitary. That's A star equals A transpose. So first thing we need to do, I guess, is find the matrix representation of T. So we have T of WZ equals 2Z minus W, okay? And so T of we have it here. Our matrix should be 0, -1, and 2, 0. Okay? So that's sort of just taking out, okay, if we have T of 1, 0, what do we get? T of 0, 1, what do we get? Okay? Now then, we'll get this as our matrix. And then all we have to do now is find, okay, what is A star? So A star is the conjugate transpose, okay? So in that case, it will just be 0, 0, -1, 2, okay? And then in order to find whether it's isometric or not, remember that's equivalent to showing whether it's unitary or not. Unitary means that A star equals A inverse. So it's equivalent to saying that A star A equals the identity matrix. And you can see that if we actually multiply it together, we don't get the identity matrix. So it is not isometric. Further, in order to see whether it's Hermitian or not, okay, the question is it equal to its conjugate transpose? And it's actually not equal to its conjugate transpose. You can see that they are different, okay? So they're not the same, therefore not Hermitian. All right, so now sort of the last idea here in this topic is the method of least squares. So this arises when we have a system of linear equations with fewer unknowns than equations, okay? So there's no exact solution, but the question is, can we find the best solution? So in terms of the best solution in the least square sense, this is sort of what minimizes the error. And to do that, we find, okay, in which case is ax minus b minimized, or it's the smallest norm, okay? So we can see that the least square solution will satisfy this, okay? Or it's the solution to this linear system of equations, okay? In Math2501, we replace the adjoint with A transpose, okay? And so now it's just a matter of, well, I guess in terms of finding the least square solution, it's just a matter of actually solving these equations, okay? So let's look at an example here. So an engineer is trying to fit a simple waveform to a signal. She has measured the following responses at given times t in the form tx. So we have these set of data points, okay? Now, if the engineer is trying to fit a curve of the form a cos t plus b sine of t to this data, what values of a and b will she get? So the first step of doing this is to write down the system of equations that we're solving, okay? Now to do that, we'll just sort of take this, okay, and plug it into our, I guess in this case, our sinusoidal fit, okay? So if we actually plug that all in, we'll get this system of equations, which can be represented in matrix form like this. So this is our ax equals b. And now remember that the least square solution will be a transpose a x equals a transpose b. And so all we need to do is multiply by a transpose to get this linear system of equations, okay? Now this is solved fairly straightforward because we know that the inverse of this matrix will just be 1 on 9 times 7 minus root 3 squared times this matrix. So we swap these around and then add negative signs here. And this will be our inverse. That's the formula for an inverse matrix. And so if we just multiply that across, we'll get this is our solution. So a equals 13 on 10, b equals root 3 on 10. And so our least squares solution will be 1 on 10, 13 cos t plus root 3 sine t. Okay? All right, so now we'll move on to the final topic for today, and that is determinants. So to go into determinants, we'll first look at some ideas that are only in Math2601 that sort of fit behind the definition of a determinant. And this is the first thing we'll look at is permutations, right? So a permutation is a reordering of the set of n items, okay? In a permutation, each item is sort of sent to another item, right? So we can write a permutation in this form. So sigma equals P1, P2, Pn. And now what this sort of represents is saying, okay, 1 gets mapped to P1, 2 gets mapped to P2, and so forth, right? So if I had a permutation, for example, like 1, 2, 3, this is a, oh, sorry, that's not a great one. So 1, we'll say 1, 3, 2, 4, okay? This is a permutation on the set of the numbers 1, 2, 3, 4. So in this case, I'm saying, okay, 1 gets sent to 1, 2 gets sent to 3, 3 gets sent to 2, and 4 gets sent to 4. Okay, that's what this notation is telling me. It's saying 1 gets sent to 1, 2 gets sent to 3, 3 gets sent to 2, 4 gets sent to 4. Now, we can look at this idea called the sign of a permutation, okay? So the sign of a particular permutation is sort of an indication of how many inversions it creates, okay? So the actual sign of a permutation will be this number, which is -1 to the power k, where k is number of inversions. So an inversion is whenever a smaller number that's originally smaller in the original set gets mapped to a larger number under the permutation. Okay, so what I mean by that is if 2, I guess we'll have a fairly straightforward example here, like for example 2 1, okay, which is a permutation saying okay 1 gets sent to 2 and 2 gets sent to 1. In this case, this is one inversion, because you can see that 1 is a smaller number than 2, but you can see that how it's ordered is now it being a larger number than 2. Okay, so that's an inversion. So now the question is, how many inversions would there be in this particular case? So here you can see that we're sort of seeing, okay, where is a smaller number, okay, in a position larger than numbers that are supposed to be larger than it, if that makes sense. So for example, right, 2, we know that 2 is less than 3, right? But 2 in this example here, it's ordered after 3. Okay, so that's one inversion. Okay, we also know that I guess if we look, are there any other inversions? And so there won't be any other inversions, right? And the reason why is because you can see that other than 2, all the numbers are ordered from smallest to largest. Okay, so the only inversion will be 2. Okay. So the properties of the sine function is if I have two permutations and I apply them one after the other, the sign of that permutation will be just the multiplication of the two signs. Okay. The sign of a transposition is always -1. Okay. Oh, by the way, in this case, the sign would be -1 because there's one inversion. So a transposition is a permutation that swaps two elements. So whenever two elements are swapped, that's always a -1 sign. Okay. Every permutation can be expressed as a composition of transpositions. The sign of a permutation is -1 to the k, where k is the number of transpositions required to make that permutation. So that's kind of similar to our idea here of the number of inversions. Okay, so the definition of a determinant. So if I take a p by p matrix, the actual definition will be this, okay? So I essentially take, okay, the first element, okay, and then I look at all the possible permutations, okay, on p numbers, and I multiply all of these together and multiply also by the sign of that particular permutation. Now, this definition is not very useful for actually calculating any determinants, so we won't follow it up from here. Now, we also have this definition here, which is saying that the determinant of a matrix is sort of can be written in terms of Aij, where Aij is the ij minor of that matrix. So the ij minor is if I take an element ij here, okay, if I sort of delete that column and delete that row. And it's saying that this is a way of expressing to larger, p by p matrices, the idea that you've probably already seen before to calculate 3 by 3 matrices, the determinant, sorry. You know that to calculate the determinant of 3 by 3 matrix, I can sort of take, if I have these numbers here, I'll sort of take 1 multiplied by this determinant, and I'll take 2 multiplied by the determinants of these, numbers, and then I'll have 3 multiplied by the determinant of this submatrix, okay? So that's the sort of extension of this idea to p by p matrices. Again, this is not the most useful method to calculate determinants. Really, the most useful method to calculate determinants will be using this property. The determinant of an upper triangular or lower triangular matrix is the product of the diagonal terms, okay? So if I have upper triangular or lower triangular, I just need to take the product of the diagonal. Now, the reason why that's useful is because if I actually add a row or add a multiple of another row to one row, or vice versa for columns, determinant is unchanged. Okay, so this is sort of related to how we normally, I guess, find the reduced row echelon form of a matrix, right? So we'll add multiples of one row to another in order to get an upper triangular matrix. Okay, so this is kind of saying if I perform row operations like this, then I'm not changing the matrix. Sorry, I'm not changing the determinant. and it allows me to get to the form where it's written as a lower triangular matrix, in which case I can just multiply the product of the diagonal terms. Now some other properties here are, if I transpose, determinant is unchanged. That's related to the idea that the determinant is sort of, it doesn't matter whether you do it in terms of columns or rows, it's both the same. Okay, if you take the adjoint of a matrix, then we need to conjugate the determinant. Now, if I multiply a single row of a column by a constant a, then the determinant is also multiplied by alpha. Sorry, that's alpha. Any matrix with a 0 row or 0 column has a 0 determinant. Okay. And now if a permutation is applied to the rows of A, the determinant is multiplied by the sign of the permutation. So for example, if I transpose 2 rows, then I multiply by -1. All right, so we'll look at an example here to see these properties in action. So let A, B, C be real numbers, and let A be a 3 by 3 matrix given by this. Explain why the determinant of A equals A plus B plus C, determinant of B, where B equals this. All right, so to do this, first we kind of need to look at these two matrices. So this is A and this is B, and see what is the relationship between these two matrices. So, or in other words, how do I get from A to B? Okay. So, in order to do that, we'll sort of consider this, right? If I add if I add this row, so row 2 to row 1, what I'll get is this matrix. So we'll say, okay, add row 2 to row 1. If I do that, then I'll get on the top A plus B minus C, and then I'll have A plus B minus C, and then I'll have 2A plus 2B. Now, if we compare this right now to the matrix B, you can see that, okay, these elements are correct. These elements are correct. These elements are also correct. Okay. And you can kind of see that what we need to do is somehow factorize out A plus B plus C. Okay. And to do that, kind of remember that if I multiply any row by a scalar, then I can take that scalar out to the front. Okay. So I kind of want on the top, you can kind of see that I have 1, 1, 1. What I can do is if I can express this as A plus B plus C, A plus B plus C, and A plus B plus C, I could factorize it out to the front. And so sort of all we need to do is maybe consider one more row operation that would work. And that would be adding row 3 to row 1. Okay? Oh, sorry, and you can kind of see that also these are the same, right? So that's sort of explaining why we add row 3 to row 1. And if you do that, what we'll be left with, sorry, is this here. And you can see that what we have is this row is multiplied all by the same scalar, so we can bring it out to the front, and then we'll have this. Okay, so the second part of this is explain why the determinant of B equals this. All right, so in order to do that, you can kind of see that we have this in a lower triangular form. So we're going to have to apply some sort of row operations, right? So what we want to do is currently B, if it makes sense, currently B looks like this. And now we want to turn it into this. So what row operations do we need? So first things first, right? We kind of need to get rid of these ones, right? Now, the easiest way to get a 1 would actually be to subtract to take column 2, subtract column 1, and take column 3, subtract column 1. You can see that because if I had column 2 minus column 1, then this 1 would get eliminated by this one, and so like the same for the third one. So if we do that, then we'll be left with 1, 2b, 2c, and we'll have 0 here. Then we'll have b minus c minus a minus 2b, which gives me minus a minus b minus c. And then we'll also have 2c minus 2c, which gives me 0, right? And we'll have 0 minus 2b is 0, and then we'll have minus a minus b minus c as well. And then we'll be done. Okay? And so now, in order to find the determinant of b, you can see that we have a lower triangular matrix. So all we need to do is multiply the three diagonal entries together. And if we multiply those diagonal entries together, we'll get a plus b plus c squared. And now remember that determinant of a equals a plus b plus c determinant of b. And so determinant of a equals a plus b plus c cubed. And so we're done. So that concludes the first part of the Math 2601 seminar. So thank you everyone for coming. We'd love if you'd have some feedback form. If you'd fill out the feedback form for us, so we can work on improving these for next year. And also stay tuned for Thursday, 11 a.m. to 1 p.m. We'll have part 2 of this 2601 seminar. Yeah, so thanks everyone for coming.